Hello everyone. Today I'll be presenting this my project called Hypermnesia, Eventual Consistency in Mnesia. I would like to start by giving a brief introduction to Erlang and Mnesia for those of you who are not familiar with them. So Erlang is a functional programming language that's designed to build large and scalable systems. It was originally developed by Ericsson for telecommunications. These days, it's used by many famous applications companies like WhatsApp, Cisco, for their infrastructures. Mnesia is an embedded distributed database library. By embedded here, I mean it's integrated with the application itself and runs in the same address space, rather than say having a separate database server that talks to your website backend server through a TCP connection, for example. So here, Mnesia really runs in the same memory address space as the application itself. So this really gives it quite good performance because the application can directly access the memory itself rather than going through another layer of socket, say. Mnesia does have some problems though, and I would like to illustrate this with a simple example here. So in this example, imagine we have 3 nodes, and they are supposed to be replicas of each other, and they are holding some kind of set-like data structure. So say initially they all hold the element X, and then there's a partition that happens between AB and AC. So now you see the link between AB and AC is broken. At the same time, 2 clients are trying to insert elements Y and Z into node B and A respectively. Because the communication is broken between A and B, this insertion of Y cannot be propagated from B to A, and the database is in this kind of inconsistent state because node A is holding element X and Z, while node B is holding element X and Y, and so is C. And when the partition heals, you would imagine the database or Mnesia database to do something to somehow maybe reconcile these conflicts, but really Mnesia doesn't do anything about this. It just logs an error message onto the console and telling the user or the developer that you need to resolve these conflicts manually. This is indeed confirmed by the documentation of Mnesia, which says determining what data to keep after a communication failure is outside the scope of Mnesia. This has led to various issues. So one of the developers using Mnesia says, the experience has convinced us to that we need to prioritize our network partition recovery strategy. So the question I want to propose here is, can we extend Mnesia to support automatic conflict resolution? So so that in the previous example we saw, the developers don't have to just manually say restart the cluster each time there's a diverging cluster, which can be quite common in a distributed system where networks are not reliable. Okay, so there are some existing solutions that try to attempt to solve this problem. Unsplit, for example, is an external library developed to some kind of merge these inconsistent databases together. But this is a external library, so developers have to introduce this as an external dependency into their code base. And Forget is a WhatsApp's commercial solution for this problem. They are trying to. This is designed to be a kind of Mnesia replacement database rather than extending Mnesia natively. So this project is really trying to give some native solution built right into Mnesia so that developers can use it kind of out of the box, and it will be open source as well. Okay, so before I talk about conflict resolution, I just want to formalize this a bit by introducing consistency in Mnesia, or introducing consistency models in a distributed system with particular focus on Mnesia, because there are quite a lot of consistency models. First of all, transactions, which I'm sure a lot of us working in database and distributed system will be familiar. So transactions provide ACID guarantees. ACID stands for atomicity, consistency, isolation, and durability. So this is provided by Mnesia, and there's also weak consistency, which is really just saying we are going to do the best effort here, and there's no guarantee whatsoever. The data might become consistent by chance, or it might not. This is also provided by Mnesia with something called dirty operations. And then the third one is called eventual consistency. This is not yet present in Mnesia. It's defined as eventually all accesses will return the last updated value if no updates are made. So I propose this here because it's useful if we think back about to our previous example where we have 3 nodes, and then there's when the partition heals, the 3 nodes are in this kind of inconsistent state. But if we have eventual consistency, then this guarantees that if we wait long enough and not make updates to these replicas, they will somehow become consistent again. Note this is quite a high-level specification of a model, and we are not saying how we are going to do this, but we can kind of see why this would be useful in helping us achieve the goal of automatic conflict resolution. Okay, so I'm going to illustrate one way of implementing eventual consistency. There are a lot of other ways as well, but in this project I find this way quite simple to Mnesia because it's similar to how Mnesia currently works, essentially. So I'm going to introduce something called a set CRDT, or conflict-free replicated data types, in particular an operation-based set CRDT. So intuitively, the idea here is we send operations from one node to another, and a set operation-based set CRDT guarantees that as long as a replica or as long as multiple replicas receive the same set of operations, they will be in the same state. So this gives us convergence property and hence eventual consistency. Okay, so same setup again. We have 3 nodes. Each of them is initially holding element X. Now, suppose the network partition happens again, and clients trying to insert elements at the same time. This time we are going to buffer the insertion operation because we are doing operation-based CRDT. We buffer the operations during the partition and then send them again when the partition heals, essentially. So here the insertion of or addition of Y is buffered at node B. And when the partition heals, these operations will be propagated to each node. And by the properties of operation-based CRDT, as long as each replica receives the same set of operations, they will converge towards the same state. So finally, we get a consistent state again for each node. So here's a benchmark result. We have throughput and latency compared against the number of generators or number of clients per node. For throughput, the higher is the better. So we compare 3 operations: dirty, easy, and transactions. Dirty and transactions are built into Mnesia, and easy is introduced by this project. We see that as we add more clients, the throughput generally increases because we are adding more operations to the system, and the system can be scalable towards the added workload. And for latency, usually it's lower the better. The lower the better. So, but the generally, as we add more clients into the system, the latency would increase because there's more overhead or more requests to process. But the EC operation, or eventually consistent operation, generally stays relatively stable, even if we are adding more generators or clients to the system. Finally, I just want to show you some example code of using this API. So on top here we have a API call called Mnesia activity. This is the way Mnesia is designed to access the database. So we are specifying async dirty here. So async dirty is saying we are doing an asynchronous dirty operation, and then we are going to write something to the table, a KVPSA, and then read something out of the table. This is the top one here is built into Mnesia and how Mnesia currently works. The second one, or the bottom one, is the extended version. So this is how asynchronous eventually consistent operation is is designed to be used. So we can just change the access context. The async dirty is called access context here, and we change the access context from dirty to easy, saying, oh, we are going to do an eventually consistent operation, and then the complexity will be handled by the underlying CRDT logic, and then the developer doesn't need to do much else in order to be able to use this API. So, in conclusion, Mnesia is a distributed soft real-time embedded database for Erlang. It doesn't come with native partition tolerance support, and we have introduced eventual consistency to be able to achieve automatic conflict resolution with CRDTs as our implementation strategy. And we saw that in the benchmarking results, the performance of the easy operation is generally 10x or even better compared to the transactions. And Hypermnesia is designed to minimize the amount of code refactoring needed to be able to use this, and we had a simple example of showcasing how this can be done by changing just the access context of the original API. And that's it for the presentation. Thank you very much for listening.